All right. All right, so let's define what logically equivalent means, and then we'll talk about the double negative property as well as a few other rules. Okay, so here we go. Remember, theory classes are all about definitions. So if you understand definitions, you'll be all right. So two statements, or statement forms, I should say, are logically equivalent if and only if they have identical truth values. For each possible substitution of statements for their statement variables. So that is to say, P and Q are logically equivalent. That means the notation you would use, sorry, equivalent, not equal. Equivalent. Denoted as P, so it's like a triple equal. That makes sense. So if you see that, that means that the P statement and the Q statement have the same truth values for every possibility, every substitution. And usually you can just look at the truth table and see, all right, well, if the truth tables are the same, then they're logically equivalent. So that's it. Okay, and here's the so testing. You go ahead and write that down, whether two statements form are logically equivalent. So the first thing you got to do, the first thing is construct a truth table for each excuse me, for each statement. Make sure you match up. Oh no, that's not true. It's fine. Number 2. check each combination of truth tables or truth values, I should say. Truth values. Of the statements, variables, to see if P and Q have the same truth values. So part A for number 2. If in each row the truth table or truth value of P is the same as the truth value for Q, then P is logically equivalent to Q. B, the other possibility would be if in some row, P has a different truth value from Q, then P is not equivalent to Q. All right. So let me just mention one more thing and then we'll do a couple of examples. First thing I'm going to mention is negations. Please note that if you negate a negation, that'd be the same as the original, right? That's like saying not P would be P. Does that make sense? Like if you said it's not daytime, you'd say, well, that means it is daytime. It's unnecessary to speak that way, but it would be logically equivalent to saying that it is daytime. And we can test it with the truth table to see, is it in fact, like we got to prove it, right? We can't just, even though we know it makes sense. The homework and the test questions would be about explaining it and showing it. So if I say P is true and or false, let's see those two conditions. Not P, negation of P would be false, right? If opposite of true is false, opposite of false is true. Now, if I negate the negation, I would come back to true and false. You see how these two are the same? This shows that both are logically equivalent. Does that make sense? Where did I put the cap? Oh, here it is. Any questions on my notes here so far?
Nope.
Okay. All right, then let me turn the page then. You guys are good. Let's show non-equivalence, an example from the book here. All right. This is example 2.1.7 from your book. Showing non-equivalence. So show is the example, show that the negation of P and Q and not P and not Q are not logically equivalent. So notice how, so we're negating the and statement, and this is saying not P and Q, and this is saying not P and not Q. So it looks like they should be the same, right? But they are not, and we will show that they are not. So here we go. So let's do a truth table for all these possibilities. I gotta do PQ, and then we gotta do not Q. Then I gotta do P and Q. Then I have to do, what else? Not P and Q. And finally, I'm gonna do not P and not Q. So let's see, let's show that they are not logically equivalent. So true, true, let's do all the possibilities here. True, false, false, true, and false, false. Okay, so opposite of P, so not P would be false. Comparing it to this guy, not P would be again false for that one. Not false, right? Now for Q, not false, not true, not false, not true, and not false. All right, you guys still with me?
Yes.
Okay, so just to see if you guys remember, for the first one, would P and Q be true?
Yes.
Okay, so we're saying true and true, right?
Yes.
Okay. Next one is true and false. What do we say about and statements? And if you
They
guys are
both have to
shut,
be true.
yeah, they both have to be true. That's true. Right, so remember, don't forget, if one of them is false, that's it, right? It's false. Alrighty, so true and false, false and true, false and false. So really, it's only true and both are true. That's how the and statement works. So now negate the and statement, meaning the opposite of all these, right? So that would be easy. Now we're going to do this, not P and not Q. So false and false. So you can see it's already not the same, right? As, oh, actually, so far it is false and true, false, false, true, sorry, true and false, true and true. Okay, make sure we did that right. So, and those two, false and false, false and true. So they're all false except the last one. Do you see how these are not the same? Right? This right here. This shows they are not logically equivalent. So if I asked you to show me, is something logically equivalent or not, do you see what you have to do?
Yes.
Any question on this? I know for a lot of you, it may be a very different kind of math class. So please don't be afraid to ask me stuff.
Not from me.
Let's see here. No, okay. All right. So almost at the end of, oh, kind of, yeah. About 70 something percent done with 2.1. So let's talk about De Morgan's laws. This is an important rule. So the negation, so number one, the negation of P and Q is logically equivalent to not P or not Q. So you actually negate the, what's it called? Conjunction. Okay. You see that? That's why these were not the same, because this was still an and. And we showed that. So not P or Q would be the same as not P and not Q. All right. So I won't give you the long definition. I think this is enough. So you can save some time here. But let's apply it to an example. This example, 2.1.9. We're applying De Morgan's law. So write negations for each of the following statements. So part A, John is 6 feet tall and he weighs less than 200 pounds. What is the negation of this statement?
John is not 6 feet tall and he does not weigh less than 200 pounds.
It's close. We have to negate the and statement as well, right?
So that becomes or.
So De Morgan's telling us negate the statement. So P is what you said, right? John is 6 feet tall. Q is he weighs less than 200 pounds. So this would be John is not 6 feet tall, or how do we negate this guy?
He does not weigh less than, he weighs more than 200 pounds.
Yeah, because this is a less than 200 symbol, right? So it would be, the opposite would be
More than?
yeah, let me, it was actually, I'm sorry, I wrote it wrong. It's supposed to be at least, but yeah, if it was written correctly, you'd be right. It's, I forgot. And in the book, they said at least. Let me fix that so we can stay consistent. So when you read the book, it's the same. At least 200. So what is the negation of at least 200? You guys remember what that means?
At most.
So yeah, I guess that's true. Negation would be at most, right? So this means 200 or more, right? So the opposite would be less than 200. So you can't hit 200. But here it's saying 200 is fine. So this is like x is greater than or equal to 200. So the opposite would be x is less than 200. So we no longer have the equals to part. So the solution would be John is not 6 feet. Oops. Or he weighs less than 200 pounds. So just a little side note. Originally it was saying this, right? Negation would be this. Right, in math symbols. In English, it'd just be that. Any questions on part A? Okay, let's do another one. This time I'm going to give you some time to think about it. That way you can try it out too. B, the bus was not late and Tom's watch was not slow. So think about this. What is the answer here? Give you a, let's wait 2 minutes before you give everyone a chance to think about it. Okay. So what do you guys think the answer is?
The bus was late or Tom's watch was slow.
Yeah. So the bus was late. And you said, or, right? This has to change. Or Tom's watch was slow. It's not too bad, right? So that's De Morgan's law applied to this English statements. Okay. So now let's apply it to some inequalities, some math symbols. Okay. -1 is less than x and x is less than or equal to 4. So here you have to remember the rules for inequality negations while using De Morgan's law. So in the book, they show an extra step. So let's go and show that. So this is technically so if we negate this guy, this is like saying P and Q, right? And Q, meaning that the answer would be not P or not Q, right? Using a little side note here. Using De Morgan's law, that's what we would say. So we could just say -1 is not less than x, or x is not less than or equal to 4. That's technically true, but that's not very, but we need to go one more extra step and show the correct symbols. So if -1 is not less than x, you would have to use the opposite symbol, right? So this would be the same. So -1 would be greater than or equal to. So you use the complete opposite. Or x is greater than 4. See how I no longer have the equal to part. Does that make sense?
Yes.
So make sure you use the correct symbol. Let's do another one. No, if we have another one here. Let's make it up. And let's just ignore that. This probably is a false statement. What would be the negation using De Morgan's law?
-4 is not less than or equal to x.
And then this would become and, right?
Yeah, is it just, oh, it's just a negation? So it'll just be not?
Yeah, technically that would be the first step. So you could say greater than or equal, not greater than or equal to 7. Right, but we should use the correct symbols. So it would be the opposite of greater than.
Less than, and then equal to, right?
Yeah, we have to add that equal to. And if it has it, then you take it away. Are there any questions on inequalities? Okay. Alrighty. They mentioned a couple more things and then we'll move on into 1. All right, so the next, let's write the definition for, so this is on, this is on tautologies. And contradictions. Definition. A tautology is a statement form that is always true, regardless of the truth values. Of the individual statements substituted. For its statement variables. A contradiction is a statement form that is always false, regardless of the truth false regardless of the truth values of the individual statements substituted. For its statement variables. Okay. For example, 2.1.12. Show that P or not P is a tautology. And P and not P is a contradiction. So P or not P is pretty obvious if you think about it. Like if I told you right now it is raining or not raining, well, that is always going to be true, right? So that would be considered a tautology. So if you use an or statement with P and its negation for any P, always true, no matter what value you give it. This one is also kind of clear if you think about it. Not as clear as the first one, but P and not P is a contradiction because let's assume P is true, the negation would have to be false automatically, right? So, and no matter what combination you choose, they will never have, you will never see where they're both true, right? It's always going to be one or the other because it'll keep swapping, which means it'll be a false statement. But let's go ahead and prove that, right? So P, not P, P or not P, P and not P. So we'll have true, false, negation of that would be false, true. So true or false, as long as one of them is true, it'll be true. False or true, well, that's still true. So that shows us right here, guess I don't need that much space. This right here shows us all T's, right? Therefore, tautology. So P and not P, so true and false, false. False and true, false. So that shows us right here, all false, right? Therefore, contradiction. Okay. So if they tell you that some statement is a tautology, then just put all T's for every possibility. If they tell you a statement P or Q is a contradiction, then you should put all F's when you're building a truth table. All right. Oh, yeah, you'll need this. Just a lot to write though. Okay. Theorem 2.1.1, logical equivalences. Given statements P, Q, R, well, I can find the shit right over here. Given statement variables P, Q, R, a tautology T. What do you
Could you pick up the paper real quick? My
Oh.
bad.
Oh, thanks, man. Appreciate it.
Thank you.
Tautology lowercase t, contradiction lowercase c. The following is true. So here is the commutative law. So P and Q is the same as Q and P. Also, P or Q is the same as Q or P. Number two. Associative laws I think it'll be faster if I just send this to you as a scan. This will be a PDF later. Give me 1 second, actually. You can do it now. There's like 11 of them and they have pairs, so not about that life. One moment. This is page 49, chapter 2. Okay. Here it is. Here are the properties. I'm gonna just have it open. And I'll share it with you as well on the screen for a moment. But please save that file that I just sent you. This is what I just sent you. So commutative law, P or Q is same as Q or P, sorry, and it's just the same for or. Associative means you can move around the parentheses, just like multiplication, right? I can multiply the R onto the Q and P, or I can distribute P and that, Q and that, or I could do P into both, either way. Move the parentheses around. Distribute, so I can distribute the or statement onto an and statement onto an or statement. So P and Q, P or, and then or P and R. So see how we distribute. So if this was like plus and this was times, you'd have P times Q plus, right? P times R, same thing. Just picture, in this example, picture this is my plus and this is my times. And then the opposite is true. Okay, so whatever's in here goes there. Whatever's in here goes there. Okay. Identity laws, P and a tautology, T is equal to P, logically equivalent to P. P or a contradiction is logically equivalent to P. So all these will be very helpful when you start doing like more complex problems, which we'll do in a second. Any questions on this? On the file I just sent you? Okay, well, let's try this complex problem, see how it goes. All right. This looks a little complicated. Let's see how it goes for us. Example 2.1.4. Actually, 2.1.14. So this would be basically like almost like a little mini proof, I guess. So show that not P or Q, that's right, and Q. And P or Q is logically equivalent to P. So you need to prove that you can get from here to P using those properties. So use 2.1.1. All right, so let's do this together. Well, I know that we can, if we negate that nonsense. Well, let's think about this. Yeah, let's do De Morgan's law first. Right, so if I negate this guy, so basically when you do these kind of problems, I want you to just pick a side and try to get to the other side. We're not gonna pick P because trying to figure out how to get from here to this complex thing would be a lot harder. So don't do that. Pick the most complex side and try to simplify. That is the easiest route. Okay. So De Morgan is the first thing we should do, not this statement. So that'll be P or not Q. And P or Q, right? So that was De Morgan. So that's what we used. Should be a space in De Morgan, but who cares? Now, okay. So now let's try distributing, right? So let's pull up that thing real quick. Distributive. So right now it's like we have a FOIL, like a multiplication problem. So we're going to multiply P times one thing and then that Q times the other. So we have currently an AND statement. So what I suggest, let me look at this formula real quick. So we're going to have P, let me show more work because the book doesn't show it. And so P and P times this, or in other words, P and all this will be P or Q, right? Plus, really, or I'll switch back in just a second. Not Q times P or Q. Let me switch back. Is that clear? I know this is a little weird, so I'm trying to pretend it's pluses and times and multiplications and pluses. Any questions so far? All right, let's see how this goes. Sorry, one moment. Okay. P and P or Q. So I'm gonna have to distribute this nonsense over here. So I'm gonna have P and P or P and Q, right? Doing my multiplication here. Or I forgot a symbol, shoot. This should be an and right here. Not Q. Or P, not Q. Oops, that should be and. Trying to add more steps. All right. Now, is there a property look at that PDF? Is there a property for P and P? Actually, I think I see a better route. I think I took a long path. Give me a second. And let's just go with it. Let's see what happens. So in the notes, in the thing I just sent you, P and P is equivalent to P. Let's see what happens. Sorry, guys. There's something that I'm missing. Give me one moment. No, I guess it has been an hour. Take a short break here. Come back in about 10 minutes. Be right back. Real quick. I missed the easy step is what happened. So you guys were with me up until the Morgans, right? No, check this out. This is pretty silly. I can't believe I missed it. So the distributive law. So right now we have this going on. So we reverse this in this direction. So we have P, or actually we have this one. P or Q and P or R or whatever, then we just reverse it. So we're gonna get, right? So we're gonna get, I thought I'd jump on there from my erasing. P and not Q and not, or and Q. All right, so look at this closely. Oh, please open your PDF so it's easier. So this Q goes here, this R goes there, and this P, double P, it's almost like you're factoring the P out. It's hard, it's weird to think of it that way, but it's just the closest they compare it to. So once you're here, it becomes way more simple. Because Q, not Q and Q, is a contradiction, right? Remember we said that? So that would be P and C, or sorry, P or C, which would mean it is equal to P. Then that's what we wanted to show. Are there any questions on how we got there? Because we're out of time. I thought we could take a break and then continue for another hour, but I was mistaken. Because I'm dumb. Okay, but anyway, I was trying to distribute all this, but instead I should have just factored, gone in the opposite direction. That was the problem. I didn't see it at first. Okay, well, let me assign you some homework and then we'll call it a day. One through five odd. Yeah, let's say 9, I guess. Well, then do 17, 21, 23, 25 through 31 odd. $35, 37. Okay. $45. Now the most important part would be 50, 51, 53. These are for sure have something like this on the test. It's like the last one we just did. All right, so I'll scan this and send this to you really soon. Guys have any questions before we stop? I know we went a little over, but it's okay. Okay, so we'll start 2-2 and see how far we can get. Sadly, we only have 4 to 5:15. I wish we had more time, but oh well. I guess, well, if you have no question, you're welcome to head out. I'll see you on Wednesday for 2.2.
Thank you.
See you later.
I have a question.
Mhm.
Where are we turning in this homework?
So I'm going to create a little section where you can upload your work. So what I want you to do is scan it and then just upload as a PDF.
Okay, thank you.
So I haven't made it yet. So, but you'll see it in Canvas soon under modules.
Okay.
Bye.